Well, welcome back to videos. It's been a little while since we've had a new one, and hopefully with some of the feedback that you guys gave me on the earlier videos, we can make these going forward better and better, and try to make them a little more effective for everybody. We'll give it a try. As you see there on the opening slide, today's topic is with matter, its properties and its changes, as well as how we classify matter. So that's how we'll start things off, and I think you'll find that this unit has a lot of contrasting terms, so I'll kind of point those out to you as we go along, and it can, I think, go a long way in helping it make it easier to get the ideas straight, keep the ideas straight, and not confuse things as you go. By the end of this video, hopefully you can tell the difference between chemical and physical changes, chemical and physical properties, intensive and extensive properties, as well as the differences between mixtures and substances, compounds and elements, the terms heterogeneous and homogeneous, and what a phase is versus an interface. Now, I wouldn't write all these down here as a list because those will all be coming later on in the video, a bit at a time, and explaining each of those pairs to you as we go. But as I say, as you go through this unit, you're going to find a lot of these paired terms that are not necessarily opposites, but they kind of go together and complement each other, and we use them to kind of separate things into these two classes or these two categories a lot of times. So as we go, keep those things in mind. Well, we'll look at properties last. Properties are fairly straightforward, and they're basically just characteristics of matter. So we can describe matter by talking about its properties. More or less, it describes the appearance of matter or a material, or it describes the behaviors of a type of material. And so that might describe any of those changes that it goes through. How does it melt? How does it react? How does it boil? How does it dissolve? All kinds of changes that can be described by the properties of a material. And so we use those to describe it throughout the lab. If in lab you're making a material change into something else, you want to be able to tell that it's changed, and you do that by looking at its properties. If its color has changed dramatically, you probably know something has changed. And if it hasn't, then maybe you have to look for texture changes or a state change. So the properties are what matters in terms of describing how something looks and being able to communicate what things have happened, using properties as sort of those adjectives. There are two kinds of properties, just like there was with change. There are chemical properties. These describe the qualities or behaviors that can often be seen only by changing the substance. So unfortunately, it's kind of hard to prove certain chemical properties without wrecking the material that you start with. For example, it's hard to prove that, say, a piece of paper is flammable without burning the paper, and at which point you no longer have the paper. So sometimes it's hard to prove these without destroying what you've got. Not that that's a real big deal, and a lot of times you don't have to because people just know that paper burns. But to prove flammability, for example, it often means destroying something that you're proving. Or, for example, a metal's ability to rust, which is really only going to happen for iron, or to oxidize, which is the more general term. Most metals can oxidize in some way, and so we can describe the ability for copper to tarnish or silver to tarnish or oxidize. Alka-Seltzer, you saw the picture before, reacts in water to make a gas. That's a chemical property. You're describing how Alka-Seltzer behaves and how it changes to make something new. At the same time, we can talk about something like plastic. Plastic does not rust. No kidding, you're thinking. Well, that's also a chemical property because it's resistant to rusting. So a lot of times, chemical properties can be those things that don't happen as well. A change in the matter that doesn't necessarily happen, or a change that matter does not undergo. Plastic does not rust. Well, obviously. Wood does not dissolve in water. Okay, that's talking about a property that does not happen. So a lot of times properties, both chemical and physical, can talk about things that don't change as much as they talk about the things that do. And of course that's important because we don't want everything to rust. We don't want everything to react with acid. Otherwise, how would we store acid? So the properties that do and don't happen are both super important. The other kind of property is a physical property. Physical properties describe often qualities that can be observed without changing the composition. So as we're looking at a material and describing its physical properties, usually those are things that are very outwardly obvious, like color. We can mask something without changing it. We can test to see whether something conducts electricity or heat without wrecking it. We can test something for its boiling point, and we haven't changed it into anything new. We've changed the state, perhaps. We can measure density. We can observe and feel the texture. All those things are physical properties, and you don't have to destroy anything to test these things. They're all still going to be there after you've shown these properties to be. So they're not quite as flashy, but they're very important again. And this is just a partial list, of course. Physical properties can actually be divided into two groups, so we separate those out into two contrasting terms as well. The first is an intensive property. Intensive physical properties are those that are independent of the amount of matter that you have. So for example, color. It doesn't matter how big the sheet of paper is. If it's a blue sheet of paper, you can tear it in half, it'll still be blue. You can tear off one little corner, it'll still be blue. So that property is independent of the amount. We can look up copper's density on our periodic table or in the back of our lab book, and it's right around 8.92 grams per cubic centimeter. That's true no matter how much copper you have. A big chunk, a little chunk, it's going to have a density that's the same. The melting point of ice is 0 degrees Celsius. That's true whether you're talking about a little ice cube or an entire sheet of ice. It's going to melt at the same temperature every time. And conductivity. Copper wire, for example, conducts electricity very well. And it doesn't matter if the piece is 6 inches long or 6 miles long, it's going to conduct fairly well. And so conductivity is an intensive property. On the flip side, there are extensive properties. And those are things that do depend on how much you have. So for example, if you measured the mass of a piece of aluminum to be 10 grams, and you write that down, and then you cut that piece in half, well, you're only going to have 5 grams in that piece now that you've got left. Its mass has changed, its volume has changed, the length of that piece of aluminum has changed. All of those would be extensive properties, but none of the intensive properties would have changed. It would still be sort of, silver metallic colored. It would still have a density right around 2.7 grams per cubic centimeter. It would still have the same melting point. I don't know that off the top of my head. I know it's pretty high. And conductivity would still be what it is for aluminum. It's pretty good. So all those intensive properties would be about the same. Wouldn't have changed at all, really. Extensive properties would all be affected. So extensive properties do depend on the amount of matter you have, and there really aren't too many of those. Mass, volume, length, those dimensions, and that's really about all. So it's a pretty short list. Just to note, make sure there's no misunderstanding here, all chemical properties, like flammability, okay, like the ability of a metal to rust, all of those are intensive. We never have extensive chemical properties. So for example, wood. Wood will burn no matter how big the piece of wood is. It could be a toothpick, could be a whole tree, it'll burn if it's dry. Iron will rust. It doesn't matter if it's a tiny little nail of iron or if it's the hull of a Titanic, which I think is iron. I should look that up. But it's going to rust no matter how big or small the piece of metal might be or iron might be. And so all those chemical properties are intensive, never extensive. So as we wrap up, keep in mind then all these contrasting terms, and there are more just in what you've written down in the last few minutes here. Mixtures versus substances. How do we compare those two? Compounds and elements. Heterogeneous, homogeneous. Phase and interface. Chemical physical change. Chemical physical property. Intensive, extensive. All these different terms that we see paired up. Whether that's helpful for you or not, I think it's good when you have these contrasting terms, because if you understand one, the other one might kind of come along with it. To some extent, they're kind of opposites in some cases, but other times they're really not. Compounds and elements aren't opposites. Phase and interface aren't opposites. So when we're looking at these, it helps to have pairs. If they're not always opposites, we don't want to slip into that assumption, but helping to keep them straight in your head with terms as pairs might help. So that's that. Today's video sponsors were 3 mixtures, actually. And since it's Halloween night and I've got lots of leftover candy, I thought I'd share them with you. First sponsor is 3 Musketeers, which is an okay candy. It's pretty boring. And the reason that I think it's kind of a boring candy bar is that inside it's quite homogeneous. I don't know if you can see that very well in there, but it's kind of the same, whatever that is, fluff through and through. Now you can think about the chocolate on the outside, that's a different phase, but the inside of it's very homogeneous. It's just this kind of tannish fluff. Yeah, it's not bad. There are better candy bars. Snickers bar, for a long time, was my favorite. Let's take a look at that one. Oh yeah, see there, we got Heterogeneous. I don't know how well you can see this either, but inside we've got at least 3 different phases. Caramel phase, that bottomy, I don't know if that's a nougat, a cookie phase, I think that is down there. And then there's peanuts in there. I'm not sure if any of those are visible, but at least 3 different phases. Much better, a heterogeneous mixture. And again, that's the Snickers corporate sponsor. And In my opinion, the king of all candy bars is the Humble Twix. I like the peanut butter ones, but the caramel ones are pretty good. Probably my favorite one. And the Twix, of course, has a cookie layer on the bottom, which is really awesome. And has that lovely interface between cookie and caramel. Oh, phenomenal. A great candy bar. The way to Bleth's heart is through a Twix bar. And a good cup of coffee, which I'm out of. So, there you have it for the night. As you sign off and I sign off, I'm going to finish my corporate sponsors and head to bed. So, you have a great day. And if you have any questions, write them down. Go back to the beginning of the video if you want to make sure you can still answer those questions. Tell the differences between those different terms. It'd be a great idea. And we'll take it from there.